You probably already know this, so I'm going to say it really fast. The frequency of a sound wave is associated with pitch, that is, the higher the frequency, the higher the pitch. Got it? Got it. Musical notes are represented by the first 7 letters of the alphabet, which in case you didn't pay attention in kindergarten are A, B, C, D, E, F, and G. In between any notes, one can find a sharp or flat. That means, for example, that in between C and D lies D flat, a note that has a frequency right between that of C and D. If you've ever seen The Sound of Music, you know the song that goes, Singing do, re, mi, fa, sol, la, ti, do is singing a major scale, a pattern of notes with waves of increasing frequency. When Maria and the 7 children she babysits get from the low B flat to the next B flat, that is an octave. I have asked my friend Sarah to help me with the demonstration. Okay, you've seen it, so now we can explore it. The reasons the notes sound the same but higher or lower is because their frequencies are multiples of each other. For example, the 4th C note on the piano, middle C, has a frequency of 262 Hz, and the next C has a frequency of 524 Hz, double that of middle C. Now that we've covered the basics, let's move on. When you want to create a chord, which is a series of notes played simultaneously, there are only certain notes that create those chords. Chords always have a desired harmony in mind. Because if 2 random sounds occur at the same time, you wouldn't automatically call them harmonies, would you? That's just noise. Here's a great example of just noise. Now then, what makes harmonies harmonies? Why do the notes sound so amazing together? Well, that's because their frequencies have certain ratios. In a major chord, the ratio is 4 to 5 to 6. Doesn't it sound happy? Hypothetically, the bottom note could have a frequency of 8 Hz, the middle note could carry 10 Hz, and the third note could be 12 Hz. This is what a major chord sounds like. Allow me to show you with the a cappella app. Expo. A minor chord is different. It sounds much more solemn. It's pretty similar to a major chord, except the middle note is just slightly lower. Its ratio is 10 to 12 to 15. I have enlisted the help of my non-computerized self for the next demo of a minor chord. Now, there are a whole bunch of other chords to talk about, but now that you get the concept, I get to show you the chart. Take a look at the ratios for diminished chords and 7th chords. Here's what a diminished chord sounds like, and here's what a major 7th chord sounds like. Alrighty, it's time to talk about waves. Sound waves are compressional waves, which means they compress the air. Do you hear it? Waves we're talking about are standing waves, which look like this. Ends of the footballs, those are called nodes. In between 2 nodes is an antinode.
There are 2 different types of nodes. There are pressure nodes and displacement nodes. No, we're not talking about this one. We're talking about these kinds of beats, but we'll get to this graph later. Beats are the constant constructive and deconstructive interference with 2 sound waves. This graph, graphed by this function, shows us the amplitude changes, which gives us that wub sound. But this graph is a perfect graph, and not everything in this world is perfect. What you heard looks more like this. In order to find the equation of the standing wave, we will need to find A, B, C, and D. D is the frequency of the function, and we can find it by using the equation 2 pi over period. To find period, we sketched the graph and found that the period is about 1.2 seconds. We plugged in period for t and got the frequency of about 5.236 seconds. D was given to us by the program. Pressure nodes tell us the change in air pressure in the air column, and displacement nodes tell us the displacement of the air particles in the air column. At a pressure node, there must be a displacement antinode, because if there's no change in pressure, then the air must be moving freely in the air column. There are 2 different types of air columns. Open-ended, which have both ends of the tube open like a flute, and closed-ended, which have one or both ends of the tube closed like a recorder. Wavelengths vary for each air column and each harmonic. In an open-end air column, the distance from antinode to antinode is half a wavelength. So in the first harmonic, we get that 1/2 wavelength equals L, and then when we solve for wavelength, we get that wavelength equals 2 over 1 L. In the second harmonic, each node is a third of the distance, so we get that 2/3 wavelength equals L, and then wavelength equals 3/2 L. If we keep doing this, a pattern of wavelength equals 2 over the number of nodes L. This is because in an open-end air column, the distance from antinode to antinode will always be 1/2. In closed-ended air columns, the situation is a little bit different. In the first harmonic, the distance from node to antinode is a quarter of a wavelength. So that means that wavelength equals 4L. If we go to second harmonic, we will find that it does not exist. This is because if we add another quarter wavelength, we will not be able to hear the tone from the instrument. This is true for all even-numbered harmonics in a closed-ended air column. In the third harmonic, we add a quarter plus a half, which gives us a wavelength equivalent to 4/3 L. And in the fifth harmonic, we add a quarter plus a half, which gives us a wavelength equivalent to 5/4 L. What does this information tell us about the pitch of the note? Well, this formula tells us frequency equals velocity over wavelength. Velocity will always be constant because the sound wave is always traveling through the same medium. Wavelength will change based on the harmonic. The lower the harmonic, the bigger the wavelength, and the bigger the wavelength will result in a lower frequency. And we reviewed earlier in this video that the lower the frequency equals lower the pitch. The following demo will accurately demonstrate this information. Have you ever played two notes that are right next to each other on a piano and gotten a sound similar to this? Those are called beats. And after playing around with some numbers, we found that the equation is y equals plus or minus 0.1 times sine of 5.236x plus 0.9 plus 2.8. Now we'll give it back to Sarah to tell us about tone color.
Tone color is essentially a quality that allows one to hear the difference between instruments that play the same note, aka frequency, for the same amount of time, rhythm, at the same volume, amplitude. For example, the A note on a clarinet sounds different from the A note on a trumpet. Tone color depends on the material with which the instrument is made. It also depends on the way the instrument, or even set of vocal cords, resonates. Tone color demonstrates the difference between music and noise. When you drop a pencil, it vibrates at a varying number of frequencies, whereas when you play a music note, it vibrates at one frequency. There is a whole number definition for music, whereas there is no whole number definition for the varying frequencies a person perceives when a pencil hits the ground. Thank you so much for watching our expo on the physics of music, harmony, and winds.